Hello everyone, I am Horichi from Development Center 3. In this session, I will present titled High-Speed Distribution to Enormous Group using PubSub of Redis. When there is a major update or release a new feature, don't you get worried whether the system is working properly or failing? Even if you don't, you may wonder if your system is working properly. We also worry about it and frequently look at the logs and metrics. While looking at the logs, we see error logs and warning logs that don't need to be output and analyzed logs. I guess the other hard part is infrastructure and network failures. It's scary because these things happen all of a sudden. However, if the system is designed to anticipate such events to a certain extent, it can be automatically restored, which increases the sense of security. Today, I'd like to introduce you to some of the features we have devised in anticipation of such failures. This is enough for preamble for now, but let's start today's agenda. First, I'll give a brief explanation of what linedevday is, and then I'll give an overview of the linedevday chat system. After that, I will talk about the main topic of the day, which is an architecture for synchronizing and distributing settings in the order of old to new. The new architecture is also intended to be used to develop new functions, so I will also tell you what use cases can be expected. I will also tell you about some of the things we've done for fault tolerances in the new architecture. Finally, I am going to show you how it works in real operation. First, let me explain linedevday. Linedevday is a live streaming service that allows celebrities, famous people, companies, and other general users to freely broadcast live. Fans can not only watch the distributor's delivery but also support by sending cheer items and free hertz. You can also use the comment function of the chat to talk with the distributor and the viewers. Viewers can communicate with each other too. And since live streaming is a live thing, if you can't enjoy the moment, it's meaningless. Both the distributor and the viewer must be in the moment when using the service. And if something goes wrong or there is an operational error, all the live transmission scheduled at the time will fail, leading to a major accident. If this happens, not only the distributor but also the viewers who are looking forward to the event will suffer. It is a sad and painful time for everyone, including service providers like us. This is why we, as service providers, need to make it easier for people to enjoy real-time communication. Today, I would like to focus on the comment function of the chat and talk about the new system to achieve higher real-timeliness. As I have mentioned many times, real-timeliness is a very important element of linedevday. So I would appreciate if you could keep it in mind as you listen. First, I'll give a brief explanation of the core of the linedevday chat system so that you can get to know it. The chat server uses the accurate actor model to achieve parallel processing. Chat supervisor, chat room actor, and user actor, which are surrounded by actor actors in the figure, are the actor actors. Next, for the communication between the client server, WebSocket is used to enable mutual communication. In the figure, client 1 sends comments to message handler, and messages sent from other clients are sent from the user actor on the server to the client. There are currently 120 chat servers in linedevday, so we need to share user comments between the servers. This sharing is done using PubSub in Redis. This is a part where chat server 1 and 2 are using Redis to publish and subscribe. The publisher shares the comments sent to it and also temporarily store them in Redis. The reason it does not store the comments directly in MySQL is that it prioritizes performance. However, the comments temporarily stored in Redis will be normalized in behind-the-scenes batch process and stored in MySQL on a regular basis. Finally, the chat system can also control comments using information configured by user or the system. The main topic of this talk will be how this configuration information is synchronized between the 120 chat servers and reflected in the control of comments. This completes my explanation of linedevday and the chat system. I will now move on to the main topic of the day. How is user and system configuration information distributed to all chat servers? I will first explain the existing system and then explain the new system. Talking about the conventional system first, I'd like to pick up a use case for you to imagine. This illustrates the case where broadcaster blocks a viewer. If the broadcaster blocks a viewer, the comment of the blocked user is not displayed in the broadcaster's distribution. In this diagram, when live broadcaster blocks live viewer A, it first sends the block information to the linedevday API. The block information will be stored in the MySQL of linedevday itself, and the block information will be sent to the chat internal API server. The chat internal API server receives the block information and stores it in MySQL. After that, when live viewer A sends a comment, the chat WebSocket server will first check the block information in the local memory cache. If it exists, it will use it. If not, it will get the latest block information from MySQL and cache it in the local memory with an expiration date. In this pattern, live viewer A is considered to be blocked, so no comment of live viewer A are sent to other viewers. In this case, referring to the block information from MySQL, every time someone comments will degrade performance, and even if you use a cache such as Redis, there is a risk of running out of network bandwidth if there is a concentrated spike of comments from many viewers, so we keep them in local memory of each chat server for a limited time. I have used blocks as an example. In the past, it was not a problem as long as information set by the user could be reflected to all chat servers at a certain speed. The timing for the settings to be reflected in each server was not that critical. We didn't need to adjust the timing of the settings on each server, so we simply used local memory with an expiration date to replace it with new information when it expired. The information was retrieved by each server individually. Now, I'd like to talk about why we created a new system instead of continuing to use the existing system. I would like to introduce chat's new function for you to understand it further. linedevday has recently released a chat decoration function. This feature allows you to add a background color or a frame to your comments, making them stand out from the comments of other viewers. The decoration settings can be changed freely by users, but the change must be reflected to all other viewers in real time. Why is it so important to do it in real time and concurrentness? For instance, if you and your friends are watching a stream side by side and only one of you cannot see the decorated comments, you feel sad. In this image, I am talking about the top comments in the middle. Of course, the person who didn't see it feels sad, and his friends also question about the service. And we are also sad because we put the user in such a situation. Nothing good can come from this. We don't want that future, so we decided to create a new synchronization system. We chose to use the PubSub feature of Redis to send out information to all the chat servers at the same time. I will now talk about the new system. The main part of the new architecture is in the chat area circled in red. First of all, when the viewer sets the decoration settings, a request is made to the LineLive API server to save the settings in the MySQL of LineLive itself. At the same time, the setting information is passed to the chat's internal API server. This is same as the conventional method. Then, upon receiving the configuration information, the chat internal API server will publish it to Redis. Then, the WebSocket server of the listening chat will subscribe to published information and cache it in its local memory. Since this subscribe process is done simultaneously on all WebSocket servers, the result is that the settings can be reflected on all servers at the same time. When a viewer who has completed the decoration settings sends the comment, the chat WebSocket server can send the comment with the decoration information to all other viewers by simply referring to the settings stored in the local memory cache. Currently, there are 120 WebSocket servers for LineLive chats, but by using Redis PubSub to synchronize the configuration information of all servers at the same time, comments can be displayed in the same way to all viewers connected to any WebSocket server. This concludes how to synchronize the new settings. This mechanism is intended to be generic so that it can be reused. The next session will show you what else you can do with this mechanism. This diagram shows a use case where LineLive will send a notification to all the viewers who are currently watching some sort of broadcast at the same time. LineLive has an internal CMS for its internal operators, and the information to be notified is submitted from its CMS to sent to LineLive API server. The LineLive API server that receives a notification information will save the notification information as an operation log in MySQL and send the information to the chat internal API server. The internal API server of the chat that receives the notification information will then publish it to Redis. Chat internal API server that receives the notification publishes by listening and obtaining published notification and send the notification information to all viewers. By sending notification information this way, it is possible to send notification to all viewers at the same time with almost no delay. For instance, in this case, it will be possible to create a function to give something away on a first-come, first-served basis, which will expand the possibilities for service planning. I hope you can now see how easy it is to use the new system for other services. This concludes how to synchronize and distribute configuration information. I'd like to take this opportunity to introduce another mechanism that we have implemented to improve the fault tolerance of Redis PubSub. As mentioned earlier, infrastructure and network failures can happen suddenly, which is a surprise. Although infrequent, we have had cases where the Redis node was affected by hypervisor failure and the client-side failover did not work properly, causing the PubSub function to fail for 15 minutes. When this happens, it can be quite a hassle during working hours or on holidays. However, If the system is designed with this in mind to some extent, it can be automatically restored and you feel more comfortable and secure. I am happy if we can reduce the amount of work required in a difficult situation. We have created a mechanism that automatically recovers when it detects an anomaly in subscribers' connections in response to this. Let's assume that multiple subscribers are listening to Redis, as shown in the figure. In the case of LineLive chat system, this means that the WebSocket server is listening to Redis. For example, let's assume that the connection of the second subscriber fails halfway for some reason, and although it is listening, it cannot receive the published information from Redis. The hypervisor failure example I mentioned earlier, or even if it is not a large-scale failure, a small-scale network failure or instability on a single server may happen. So it is important to take this into account. For the sake of clarity, I will assume that one server has failed. In this case, the second subscriber will not be able to subscribe for a certain period of time, but when it does, it will publish itself to pin. Then, if it is listening properly, it should be able to subscribe to that pin. However, the second subscriber cannot subscribe to the pin. When it detects that it cannot subscribe from the pin state, it reconnects to Redis and returns to the normal listen state. The system is now in the state of automatic recovery. This is the end of the story how we devise fault tolerance. That's all for today. In the end, I will show you the result of implementing the new system. Overall, everything including new features are well received by users. And so far, we have been able to operate it without any major problems. In the future, we will use the system to quickly implement new features. If you think this is a good idea, I hope you will find it useful. This concludes today's session. Thank you very much for your attention.